This morning the plenary speakers will talk about the role of inland waters in the regional and global carbon cycle. And we start with the first speaker that's already on. It's Yves, Professor Yves Prairie, and he is from the University of Quebec in Montreal. And the title of his talk will be The Role of Inland Waters in the Global and Regional Carbon Balance. Do Inland Waters Matter? He received his PhD from the McGill University in the Department of Biology. And after that, he did a postdoc work. His postdoctoral work was at the Institute of Limnology in Constance in Germany. And then he returned again back to Canada, and he worked as an assistant professor and later as a professor of biology in Montreal at the University of Quebec. And he is also president of the Society of the Canadian Limnologists, and he lost 2 years ago, it's already in 2007, we had this fantastic SIL conference in Montreal, and he was the chair of the organizing committee. I will give now talk to Yves.
Thank you, Ellen. Good morning, everyone. First of all, an apology. I'm sorry I had to resort to such drastic measures as to create a strike in the public transport system so that some of you would stay here and not go and visit the beautiful towns around Nice. And second, thank you for the organizing committee for inviting me in this, to give this talk. I'd like to talk today about the role of inland waters. Well, we were asked to talk about the role of inland waters in the global and regional carbon balance, whether they matter. And a lot of what I will be talking about today emanates from a group of us who have been working at NCEAS, and although the funding for this has long ended a while ago, we're continuing to work on this. And these are some of the people, and several of them are here at this meeting. Before going into the details of that, the overarching theme of the session today really is, should the freshwater carbon cycle remain hidden in the global carbon cycle? And the first evidence of that it is hidden comes from pictorial diagrams that are found just about everywhere, either in books or on the internet. I've scanned a few here, and the role of inland waters is actually depicted to various degrees. In this one, if I can use the point, perhaps I will use the pointer. Yes. What we see is basically we acknowledge the existence of a river, but it doesn't seem to be doing anything in the carbon budget, and this has no numbers associated with it. This is an early depiction as well, where it's more or less the same thing. We acknowledge the river, but no numbers, no rows to it. Some are a bit better, like this one. This is a 2007 globe carbon cycle. We see that rivers contribute about 0.8 petagrams of carbon per year to the ocean, but that again, that's the only role that freshwaters or inland waters are given. This is already much better. This comes from UNESCO's Scope book, where not only we have a river flux to the ocean, but we actually acknowledge that river are outgassing and we have the fluxes in black are the fluxes that were believed to be there prior to industrial times, where the oceans, for example, were outgassing CO2, and now they are ingassing CO2 because the balance is downward at the moment. Ironically, the carbon cycle, the diagram of carbon cycle that puts freshwater actually in the center of it all is the oldest. It's a Scope book in 1979, and there, although there were very few numbers, although in the text there are some numbers, freshwaters were actually given a central role. And this is the current view of the global carbon cycle according to the IPCC 2007 book, and we see again some details as to how the inland waters play a role. We see that there is a component of organic carbon derived from soil and detritus decomposition that finds its way to the rivers, as well as weathering, DIC. Okay, so the question we can ask is, why is it hidden? One of the first answers that we can give is simply, well, it is too small a flux or too small a pool compared to the main compartments, such as the land, oceans, and atmosphere. These are really the three compartments that global carbon cycle people deal with. And when we look at the relative sizes, of course, there is some merit to that possible explanation, in that we have lakes only occupying less than 1% of the total surface of the globe, and the oceans being active, and as well as the land much more active as well, or at least in terms of sizes. So this is a bit of a David and Goliath story, and it's always intimidating to be telling this to oceanographers, that a system that is less than 1% of the ocean can actually have a role not quite as big as that of the ocean, but certainly in the same kind of order of magnitude. So in the ASLO archives, I've found here the first depiction of the debate between those who believe that freshwaters were important. I think this was the first ASLO meeting. I forget where that was. And we have here what I presume called early oceanographers. And I think this is John Cole as a young man. So the debate is not new. And when we started working on this idea that perhaps the role of inland waters had been underestimated, we basically framed this into the idea, well, are rivers simple Teflon or neutral conduits transporting some organic and inorganic carbon from the terrestrial, from the land to the sea? And when we simply compiled the literature values that had been published, we found that, well, it's more of an active pipe role where, if we believe the numbers that are currently used of how much carbon goes to the ocean through rivers, and we estimated from published values how much is stored in various aquatic ecosystems and how much is evaded from those same systems, well, it must be that inland waters have received about 1.9 gigatons, and only 0.9 of which reaches the oceans. So there was the first evidence that we were dealing with an active pipe. From then on, we started to refine those numbers a little bit. For example, this is how those numbers were broken down into the various compartments. And the amount of CO2 leaving lakes, for example, was based on an early assessment of the area covered by lakes and also by reservoirs. And one of our first tasks was to revise this. And in a paper by John Downey here, it was established that, in fact, inland waters cover a much larger surface than was previously thought, mostly because of very abundant but very small not ponds, so very small lakes, such as depicted in the picture. So we've basically doubled the surface area of lakes by taking into account those small water bodies. Similarly, but actually inversely, estimates that were published in the literature of the surface area occupied by reservoirs was very large, and the assessment of that is much smaller now, and this will have consequences as well in the budget. So we have begun to refine those numbers in a number of ways, one of which is to try to see how can we do better than simply use an average PCO2 value of lakes and upscale that to the globe. And this is some data from Sebastian Sobek, where we saw a very poor relationship, but still an existing relationship between lake area and PCO2. The smaller the lake, the more elevated is the PCO2. And with the magic of statistics and binning those values, we actually obtain a fairly straight line. And this is the same data. We've just binned them into log units. And I've drawn a line here. And this, although these 2 points here seem to be off the line, this would be actually a conservative estimate if we just follow that line, which is described by this equation. Knowing also that lakes follow size distribution, now a well-known size distribution known as a Pareto distribution, we can combine these, and knowing the frequency of very small lakes and the frequency of very large lakes and their associated PCO2, we can calculate a global flux by simple integration of from the smallest to the largest water body, multiplied by the total surface area. And this gives in itself an emission values, a new emission values that it is nearly 4 times, actually nearly 5 times that of the original value of 0.11. So we're now half a gigaton emitted by lakes. More revision on these numbers. A recent paper by Carlos Duarte showed that saline lakes alone emit 0.1 to 0.15 petagrams of carbon per year. And there's more evidence also that although rivers were originally included, small streams were not. And in the recent literature, for example, a paper by Batten, these two are about co-equal. And I will show some evidence of that later on as well. So that's the emission side, and I'm not even here talking about methane emission, because in terms of carbon, although it's important for global warming potential in terms of carbon, it's fairly small. In terms of carbon burial, the numbers also have been revised. Just perhaps a little known fact, that if we think that inland waters do not contain so much carbon, well, at the bottom of Lake Tanganyika alone, there's as much organic carbon buried there because of its longevity of that lake than in the soils of the entire living biosphere. So in terms of pools, lakes are an incredible reservoir as well of organic carbon. In terms of carbon storage, more at a local scale and in younger systems than Lake Tanganyika, there's typically as much carbon stored at the bottom of lakes as there is in the soils of their watersheds. And this is a surprising fact, and that's largely in part of the really high preservation. I always often use the metaphor that when you have sediments at the bottom of lakes, it's like putting your sediments or your organic matter in the fridge indefinitely. And such conclusions have been found in Finland, in Quebec, and also I just saw yesterday a paper by John Anderson, a poster by John Anderson, which says exactly the same thing in Greenland. So this seems to be a common feature, that at the bottom of lakes there's actually quite a lot of carbon buried there. Oops, the other way around. In another paper by John Downing from the NCS group, he's compiled all the carbon burial rate of different types of systems, going from really high values in farm ponds, for example, here about 2,000 grams per meter square per year in eutrophic farm ponds. For other impoundments in the hundreds, the average would probably be around 450. In In terrestrial systems, even though they occupy a much greater area than lakes, the burial values are much smaller, about 2 orders of magnitude smaller than in impoundments. And if we look at lakes, which are in various categories here, they're separated into oligotrophic, mesotrophic, and of different sizes, we get this kind of logarithmic scaling from farm ponds of about 2,000, impoundments about 400, lakes about 30, and forests about 2 to 3. So it's more or less a logarithmic decline in those categories. And so if we put those new numbers together, the picture continues to change. Now, if we sum them up for the CO2 evasion side, we go to about 1.2 petagrams per year, and on the burial side, about 0.4 petagrams per year. So this is our new version of the freshwater carbon funnel, or the inland water carbon funnel, I should be more precise. And the interesting number is the transformation efficiency, that is how much, what's the fraction of the incoming carbon reaching inland waters as actually processed, either as evasion or sediment storage, and that's about 65% so far with those new numbers. So this was one possible explanation of why it is hidden, simply because the pools were arguably too small. I think we are getting a sense that this may not be the case. A second possibility is that we don't really need to explicitly consider lakes and other water bodies, inland water bodies, because they are implicitly taken into consideration in global models as a component comprised within the terrestrial compartment. And from a global carbon perspective, that's easy to understand. This is, again, the latest IPCC report with the latest numbers. And what we see is that the role of the terrestrial system is really determined by difference. So if we acknowledge that we'll take this column here, but we could take this one. It's more or less the same thing, it's just more current numbers. If we believe the amount of carbon that we put in the atmosphere through combustion of fossil fuel and cement production, which is here in the mid-90s, about 6.4, about half of which finds its way to the atmosphere, 2.2 gigaton goes into the ocean, which leaves a residual sink of about 1 petagram. So it has to go somewhere, has to be somewhere else that we haven't taken into account, and that's the land. If we further consider that changes in land use itself generates an additional 1.6, that means that the true residual terrestrial sink, which arguably includes inland waters, is about 2.6 gigatons. Of course, all these are derived from one another simply by subtraction. Well, we can believe that in that sense, but I think it betrays what we view as an important and unimportant compartment. Yes, it's included, but I think if we had a sense already that it was quantitatively important, we would take it, we would use it in a more explicit fashion. After all, there are small arrows here, small numbers on these arrows that are taken into account. So it's not because it could be subsumed within the terrestrial side that it really belongs there. And I think that's really a question of aerial rates. And here I've just plotted a graph of what are the aerial rates of net gas exchange and net carbon accumulation rates. And the highest bar are always wet system, inland wet system, lakes, reservoirs, and same thing here, rivers as well for CO2 emissions. The big bar here is a terrestrial net gas exchange in as measured by, for example, eddy covariance towers. But these do not apply, they're fine for a very localized area, but they do not apply generally to the terrestrial. So if we look at the terrestrial sink, that bar here is much smaller. So a third reason why we might think it is hidden, and I think that's a valid point, is the magnitude of fluxes, whether it's emission or burials, are actually quite irrelevant if they have not changed since pre-industrial time. And already I think we just have to look outside, and we know that we have affected our inland waters. From the numbers that I showed earlier, we can begin to actually address that. In a way, changes, even if there have been changes in CO2 emissions from these inland waters, those are implicitly taken into account because we, again, are measuring the net difference between the two. However, if we want to know where is that terrestrial sink, well, we can look at whether aquatic components can be an important fraction of that so-called terrestrial sink. And there's a number of ways in which inland waters act as a carbon sink. First of all, because the PCO2 in the atmosphere is increasing, and that lakes in general are much more rapidly in steady state with the atmosphere than, for example, the oceans, well, the lake content of carbon is also increasing. The PCO2 is also increasing in lakes. And that's one aspect, but if you do a back-of-the-envelope calculation, that number is actually very small, in the order of 1 to 2 teragrams. Lake eutrophication, I think, is a big unknown. We know that we have eutrophied lakes, and we know that eutrophic lakes will bury a lot more carbon, but we don't have any good sense of how much increased carbon storage has been due to eutrophication worldwide. We've already estimated carbon burial in reservoir to be about 0.12 petagram. That's a new thing that wasn't there in pre-industrial times. Same thing for carbon burial in farm ponds, which is another 0.14 petagram. And now there's more and more evidence that there's increased DIC and possibly also DOC export due to land use changes. And I'll just take a minute to go through this. This is a paper by Raymond and Cole showing the increase in alkalinity export in the Mississippi River. And that has to be considered a new sink for carbon, a terrestrial sink that is transported with rivers. Why? Because that alkalinity is basically CO2 derived from soil respiration. So basically it's a terrestrial photosynthesis which finds its way into the rivers as bicarbonate ions following weathering reactions, either with silicate minerals or carbonate minerals. In the case of carbonate minerals, only half of the carbon is actually from the atmosphere, the second half will be from the rock. So depending on the balance between silicate and carbonate minerals, there will be a lesser or greater fraction that is a true sink. Now, in that same paper, they showed a very interesting relationship between the percentage of forest land and the alkalinity export. And although this was in the US, I've plotted some of our own data, and basically it follows the same thing in Quebec streams. And what it says basically is every time you deforest a meter square, if you wish, you will generate in terms of alkalinity somewhere between 10 and 20 milligrams of carbon per meter square per year. And contrary to what we think of it as a land use change, as a 1.6 petagram to the atmosphere, it is every year. That is, once you've deforested that 1 meter square, every year, as far as we know anyway, it will continue to export much more DIC. So if we take that conclusion and apply it to the area of deforested land for agricultural purposes around the world, which is very large, that gives another 0.2 petagrams of DIC per year. That should be considered a carbon sink. So I've put in read here the values that I think are very conservative that should be considered a change since pre-industrial times. So fairly large as well. I'd like to finish, take 2 minutes to talk about some work we've been doing in northern Quebec to look at the importance of aquatic carbon cycle at a regional scale. This is a map of a large area. This is about 50,000 square kilometers. This is right here about mid-latitude in Quebec. And each of these square is about 900 square kilometers. And in the landscape here, we've colored the lakes blue, the streams red, and purple are the larger rivers. And what we see in there is, of course, this is a very wet area. The average is about 15% water. And we've sampled a whole bunch of streams, rivers, and lakes in that area. And we found, of course, differences in PCO2. And we've built a series of upscaling tools for lakes and for streams in a couple of papers. And we've used those tools to upscale to the entire region. And if it's going to come, and if we look at this, what we found is that this is a percent contribution to CO2 emission by these three compartments, these three aquatic compartments. About half of it is from lakes, and about streams and rivers are about co-equal, similar to the conclusion that Baton had found as well. And this is the, if you wish, area-weighted aerial rates of CO2 evasion, 110. But if we express that over the entire landscape, it's about 18. And that's a very high fraction of what is believed to be the NEP of that forest around there. So in fact, lakes serve as big conduits to, to evade the CO2 that is thought to be primary production in those lakes. I really rarely get excited by a lack of relationship, but this one is actually very interesting. Each point here is one of those 900 square kilometers of area. And what is interesting, so this is a place where there's very few lakes, just streams. And here this is a place where it's 35% lakes covering that square. And basically, the amount of carbon evaded by these landscape of 900 square kilometers is basically flat. So no matter whether you are in an area that is very lake-rich or very stream-rich, you have basically the same amount of carbon evading the aquatic system. And to me, that's a fundamental change in my thinking, because it tells us that we should view CO2 evasion really as a property of the landscape rather than as property of the aquatic systems themselves. I invite you to come and follow the details of this story at 10:30 in Hermes by a talk by Paul Del Giorgio. And how will the role of inland water change in the future? I've just put here a slide with a few changes that are likely to occur. In fact, I had another slide, and I think it has disappeared, doesn't matter. And basically, there's lots of things we don't know yet as to how that role, which we know is already significant, will change. These are, again, some example of just what global warming will do. So I just want to conclude by saying that inland waters are not negligible, neither in terms of flux nor in terms of reservoirs, that the amount of carbon transformed has substantially increased, amounting to about 0.5 petagrams, or about 20% of the residual terrestrial sink. And at the landscape level, aquatic emissions represent a substantial fraction of the terrestrial NEP. And finally, that the role of inland waters in the landscape is likely to be further modified in a warming world. And at the end, I just want to acknowledge people and also sources of funding for some of this work. Thank you very much.